Bueno, buenas tardes y muchas gracias por estar aquí a la hora para esta nueva actividad en nuestros congresos de la Sociedad Española de Catálisis. Creo que es la primera vez que organizamos una mesa redonda o mesa participativa, como ponía en el programa, y creo que es una buena idea. Vamos a ver si efectivamente nos autodemostramos que efectivamente esto es una buena idea. Esto lo vamos a ver no solo por la participación de los participantes que tenemos en el estrado, que no me cabe ninguna duda, porque han sido elegidos, como vamos a ver después, pues muy apropiadamente, sino por la participación posterior, que yo creo que es lo que nos va a dar el éxito, ¿no? La mesa redonda o participativa lleva por título From Model to Real Catalysts. Es por esto que los participantes provienen de empresas importantes, de compañías importantes del sector de la catálisis. Okay? Then, well, it is for me a pleasure and even an honor to be here sharing this round table with three important persons coming from European companies specialized in catalysis. Well, I will do first an introduction, just for people to know who are most important activities they are developing in their industries. Then first, near me, is Mónica García. Mónica García pursued a master's degree in and PhD in chemistry and catalysis here at the University of Málaga, Spain, with research time training stay at the University of Genoa, Italy, and then postdoctoral studies at the University of California at Berkeley in the USA. Mónica has been working for Matthey, that's her current company, for 10 years and is currently working as catalyst testing lead and project manager for research and development in methanol synthesis. Then also we have with us to Tiziana Armaroli. She was born in Genoa, Italy, and he got a PhD in chemistry for engineering at the Department of Chemical Engineering, also in Genoa, the University of Genoa, Italy. He spent one postdoctorate stay at the Institut Français du Pétrole, and then at the same company, she was research engineering or doing research on materials characterization and catalysis by sulfide departments. Also, well, now he's working for Eurecat as product manager specialties. And previously, also, he was working for Accents as also product development manager. And then I will also introduce to Dr. Gerhard Mestl. He got his PhD thesis on Raman spectroscopic characterization of oxide catalysts under supervision of Professor Nothinger. Probably Professor Nothinger is an old companion of many of us here, because he was the president of the European Federation of Catalysis Societies. Then, even me, I was secretary at that time. Then it's for me a pleasure to know one student of Professor Nothinger. As professional experience, currently he's the head of Department Oxidation Catalysis at the company Clariant in Germany, and previously was project manager at the company Suchemi. Gerhard has several awards, several prizes, just to remember because of their importance, two of them. The 2016 and 17th Applied Catalysis Award of the European Federation of Catalysis Society. It's an important award granted by BP, and also the Cox Award of the North American Catalysis Society, which is also granted by the company BASF. He's author of many papers and a significant number of patents. Then after that, then I will give the word to each of them. Of course, you can speak whatever you want, seated, or even if you can use the podium. And after their lectures, people, we will open a discussion about everything they have said, or even any other question that people can be interested on. Then first, you have the floor, Mónica.
Thank you much. ¿Cómo que no está?
La presentación se carga aquí y no se carga ahí. O sea, porque hay una tipología diferente de presentación, que no importa. No.
Eso es sonido.
Eso es sonido.
Technological problems.
This is scale up.
Okay.
No.
Sí, pero ya sí. And can you change the slide? In that way, it's just a...
Ok, continuamos. Hola a todos, bienvenidos. Yo voy a hablar en inglés por respeto a mis compañeros de mesa, pero después, por favor, me preguntan en español como quieran, que yo responderé en español, inglés o como prefieran. Okay? So, I just prepared a few slides on what I do, basically what I do on a day-to-day basis on developing methanol synthesis catalysts for our customers. It's a very high-level overview of what we do, basically what I could fit in 15 minutes. But it's really, the idea is to be thought-provoking so that you then ask as many questions as you want, and I will answer as many questions as I can, okay? So what I'm going to cover is basically innovation in methanol synthesis over the years. It's a process that has been out there for more than 50 years. It's a very important chemical in the industry, so you know a little bit about it. But my idea is not to go really too much in the history, but more on how we get to the catalysts that are installed in the big plants, and you have an idea of scales from the lab to pilot to a big customer plant. So to do that, I'm going to cover a bit of the process, what are the relevant properties that we look at. Some of them you may be a bit surprised. And then a bit on the catalyst evaluation timeline. So it's about size, it's about time scales, and things like that, okay? So a bit of the history. So methanol synthesis is made on a copper zinc alumina catalyst, as you may know. And it was many years ago that it was discovered that the copper could do that reaction. But it wasn't until much later, like 50 or more years later, that the copper could have actually been used in that process. So sometimes you may have an idea, you may have a metal that works, but it may not be at the industrial scale for many years, okay? And that was the case for methanol synthesis. The actual first catalyst in an industrial process was a zinc chromide catalyst developed by BASF, and it was a very harsh process, a very high pressure, very high temperatures, okay? So in the 47 is when actually the copper zinc alumina material was developed, but they couldn't use it. They had a good material that was really active, but because of all the poisons that were coming with the gas that we needed for that process, it couldn't be used. It was too prone to poisoning. So it wasn't until much later, on the 63s, that ICI, now Johnson Matthey, they developed the low-pressure methanol synthesis process, where we could actually use a copper zinc alumina because we needed a purification section, a proper reforming section, so that we could have the full flow sheet to be able to make methanol from natural gas or from coal. And at that time, it was just from nat gas, okay? And from then, at that time, ICI patented the first methanol synthesis catalyst, which was a copper zinc alumina, and it was a 51-1 catalyst. From there, and my idea is not go through every single development that we have made for methanol synthesis, but just have an idea. We had that formulation, but we have to go through many, many new product improvements to keep going, to keep staying alive in the business of selling methanol synthesis catalysts, okay? So just to give you an idea, we started with a 51, and from there it moved from the 65 to the 90s to a 51-7. So there were at least 6 to 7 materials there. There were step changes in the formulation. The big step change there was the introduction of magnesium to the formulation, and then after that, many, many other products with different properties were introduced. So how and where do we develop catalysts in the industry? This is where I work. It's a methanol R&D team, and that's where we develop the catalysts. But we are not an isolated team in the industry. It really takes a multidisciplinary team of people to make able to put something from the lab to a much larger scale. I'm not going to go into each detail on how we interact with all these teams within the company, but it's to give you an idea of the magnitude and the number of people and specialties that have to be involved in developing a catalyst at industrial scale so that you can safely and effectively introduce a product to the market. So we are at the heart of developing a catalyst, but we need to work with many other sides, like manufacturing side is an obvious link. We also work very closely with engineers for scaling up, engineers for process understanding to translate what we find in the lab to what it will mean in a big plant. We work closely with analyticals, all the core science teams, the characterization, all those sort of things. With the commercial team, with the customers, which is very, very important. We need to understand what the customer needs. And then we also need to work really closely with legal, safety, and regulatory affairs, okay? So you may have a very good material, but you may not be able to sell it in half of the world because that substance is banned. So no purpose. You may have a material that someone else has patented, you can put it on the market, you don't have freedom to operate. So you really need to work closely with many, many other departments to make sure that you're working, will be compliant, will be safe, and you're going to be able to sell it. This is a very brief, very, very, very brief summary of the stages that you go through when you develop a catalyst. A very, very high level, okay? I'm just going to go through it really, really briefly. So we basically go through these stages. They look there like they are in that order. It may not necessarily be the case. Sometimes you need to iterate back. But normally you start with a concept, an idea, okay? So a lot of the fundamental research really comes before that. It's the basis of more of the things that we do. So once you have an idea, you may build something around that. And the most important thing that you need to build around that idea is a business case. Is this going to sell? Okay. Yeah. So once you have a business case, because without that, you don't have the green light to go after that. Okay. So once you have a business case, you go through this step, which is basically a proof of concept. You start generating your strategy on how you're going to develop it, how you're going to, so you put your project plan together, what you're going to do, how you're going to evaluate it, how you're going to launch it to the market. So even very early, you look at many things like safety, operations, what it will imply, if it's super active, can I install that in a current plant? Is it for existing customers? For new? Lots of things that you need to think about. Supply chain, this is that material, can we get the raw materials, are they a good price, are they going up, are they going down, and that sort of thing. Sustainability, big thing. Now, we all should look after our environment, make sure you make more sustainable process, more sustainable products. And process engineering, IP strategy, freedom to operate. Can I install that? Someone else already patented. Do I need to get protection? We got this brilliant idea. We need to patent it. I don't want Clariant to use it. Things like that.
We don't want to use it.
Or the way. Yeah, you know, and you'll do the same. You go through development, and that's where most of the research and lab stuff happens. There's most of the activities go there. It's really when you put that translation from lab to the pilot scale. You define what sort of synthesis you're going to do with the material. You define how you're going to evaluate it, depending on what you're targeting. And then you look at that route to, scale up route to the market, how we're going to market it, we're going to talk to the customers, et cetera, et cetera. Then you go to scale up, so you bring it to a pilot. So if you are successful, then you go to scale up. And then if you see down here, we have, there. I tried to put a bit of scale. So at this stage, it's really small size, grams, 10, 50, 100 grams, tops. You move to scale up, we're talking about kilograms, sometimes close to tons, and then you move to plant scale when you are really, you see you are able to scale it up, you have your plans, you review all your assessments. Again, this is like a really brief. This may take years, okay, depending on the product you are developing and what sort of tweak you're doing. But then you move to really like plant scale tons. It's a lot of investment involved, so you need to make sure each step is right. At each step, you stop frequently, you see your review, and you see all those functions, everything is right. Then if everything goes okay, you go to launch, you bring it to the market, you go to campaign, and then of course, hopefully the material you produce already scale up, you install it in a plant that you know that you have a really close relationship with the customer, you start getting data, and the process doesn't stop there. You keep reviewing it, you keep monitoring what you're generating. Okay. This slide here is just to give you an idea of all the properties that we need to look at when we develop a new catalyst, okay? Most of the time when I was in the lab and my PhD, we look, it's very active, the conversion is really good. It's really stable, it lasted for a week. 2 days, woo, great, fantastic. It's a bit more complex now. So apart from the obvious ones, the chemical properties that you have the right composition, then you don't have the impurities, like very low levels of impurities, it's very sparse, you have the right phases. There are a lot of other properties that we need to look at. So we can sell powders. We need to form the materials. Methanol synthesis, for example, we sell these sort of pellets. Here's the picture, tiny 5-millimeter pellets that you form. When you form it, then that brings all a new suite of properties. So you are creating a network of porosity that's going to affect performance. So depending on how you pellet it, the density you get, so that's going to affect strength, not only when you loaded it to the reactor, when you transported it, etc. And then you need to decide how you're going to shape it, what is the size, what is the effective size, how is diffusion affecting it. It's, lots of things you need to look at, especially in methanol synthesis, since we reduce it, the pellets change in size, they get weaker, so you also need to look at those extra properties in there. And then, of course, you look at the catalytic properties. It's not only activity on the formulation on the powder, it's also on the pellets and the selectivity, stability, poisoner, and stability. So to give you an idea on how we evaluate before we launch, you have here 2 different scales. I try to put a scale on how you go. So from lab scale, pilot scale, plant scale, grams, kilograms, and tons. So you have a suite of tests that you could do, and they will last in different time scales. So you could start during your lab scale, when it's mainly development, it's mainly screening, lots of material, different properties, so that you can rule out the good from the bad and go from there. But then you really need to go through all those properties after that you need to look at. So then, stability, life testing, how you're going to do. Methanol synthesis catalyst lasts for 4 years in a plant. How do I test that in the lab? We can't do tests for 4 years, so it's not feasible. It's not economical, Then my developments are going to last for 20, I wouldn't see that, so you need a strategy there. Then you also do testing at pilot scale, so it's not only in the lab where you look, grids, pellets, you also go and really smaller plants that you attach to customer plants and try to get information from there. And of course, a reactor in a customer could be anything from 50 tons to 250, 300 tons of catalyst, one plant, okay? And we come from a lab test that is with 0.5 gram. Okay. Pilot testing, half a kilo, 1 kilo, etc. So it's really big stage changes. And then my last 2 slides is just a really short example of a recent development that we made, which is about developing a catalyst that is. Our target was to develop material that was 30% more active than our previous generation materials at 3 years online, okay? And the biggest challenge there was, how do we evaluate a material that is going to be 30% more active at 3 years online? If you had, let's say, 10 materials to test, are you going to put them for 3 years? No, so you need to find a strategy to evaluate that material in a shorter time. So to that, we modified the formulation. We added an extra component and went through that, and just wanted to show you the example on how we went around that and how we were able to evaluate the material to make sure that we were meeting that target. And what we used was something called accelerated deactivation testing, in which we were accelerating the deactivation without changing the mechanism in which the deactivation was happening. So that's what I'm showing on this first plot, where in 14 days, we will see an equivalent deactivation of what a customer in a plant will see in 1 year, 2 years' time. And in that way, we were able to screen our materials. And then for that screening, we moved to a pilot scale, where we have a few kilograms of material for a year, 6 months, a year, showing a similar behavior. So what we show, this is relative activity for prior generation. So we were just one is everything above 1, and we were targeted at 30%, so anything above 1.3 at 3 years online. And this is the actual data from the first customer that took that charge, which is tons of material, and after 4 years online, we were getting that performance that we were predicting from the lab. Okay, and that's what I had. I'll leave the floor for Tiziana. Hopefully, I gave you an idea of what I do and how we develop the materials at Johnson Matthey. So it's not Tiziana, it's Gerhard first. Thanks.
Thank you very much, Mónica, for your interesting example on how to develop one catalyst from the idea until the commercialization. Thank you very much. Now, sorry.
Hopefully.
Perfect.
So it's my turn now. So thank you very much, first of all, Juan, Jose, and where is my good friend, Vicente, for having me invited to this wonderful conference. I really enjoyed it a lot, and I think also this round table is a very good idea, and I hope that I can add a little bit to the predecessor's talk. Excellent talk, by the way. Congratulations. And I hope that the presentation, we have not spoken to each other before, so still I hope that I can add something to it. And when I was invited I was thinking what to present, and of course, I could have given quite the same talk, because this is really the standard way that industry scales up into the ton regime, so every one of us has absolutely this task. Starting from the very early work that you have to do with the project management stuff until you have finally a ton or two or maybe 100. So I thought that maybe I pick something which is really new, and the other way, huh? No? But I don't see it down there. It's...
You need to leave a press for a bit.
No, but just to pass. You want to pass? No, but to pass is this.
No, I know, but I wanted to check I wanted to check the pointer, but now I see it. Okay, good. So, and I thought that I would talk about something really new, not for all of us. Behind there's someone sitting, a real expert in this reaction, and so I'm happy that I can show our work to you. And it's about the oxidative dehydrogenation of ethylene, of ethane to ethylene. And this is something that is not only a new catalyst. If this is materialized, if this is made in steel in the end, it would be a totally new process for the world. And what is the problem? The problem is here. Ethylene belongs to the most energy demanding products that are made in the industry. And that is why, this is very slow, okay? This is why ethylene belongs to those products which emit most of the CO2. And we heard a lot about these problems in the last couple of days. So it is clear that this has been studied for many, many years. So will this change in the future? No, it will not change. It will continue to grow. So despite the fact that every one of us should have, 2 tons of plastic bags at home already, we keep on producing plastic bags at a rate which is outraging. So from itself, this will not change. So we will emit tons of CO2 just because we need so much polyethylene and all the nice polymers that you can make out of ethylene. Why is this such a problem? The problem lies in the fact that ethylene is made by natural gas steam cracking. Natural gas steam cracking, especially for short-chain alkanes, is never going to be a sustainable technology, never ever, because the shorter the chains become, the higher the temperature needs to be to make it. And so you really need natural gas-fired crackers, steam crackers, to make it. And then still you are limited by the equilibrium. And so very early already, people have understood, and this is not surprising, that maybe the ODH of ethane to ethylene is a way. And this is a graph that I picked from a publication of my good friend Fabrizio Cavani, and I put in here the box, the green box, and just to show you where the target is for a ODH process that should be competitive to a world-scale steam cracker. Yeah? In terms of conversion and selectivity, you have to work here, but it's not the productivity. The productivity is what in the end counts. Yeah? So selectivity, conversion is one factor. The second factor is the productivity, and this is a problem for the ODH. Oh, sorry, back. I should say that, of course, because of the task was clear, many catalysts have been investigated, and there was a very nice poster here also. It became clear already a couple of decades ago that this very special mixed metal oxide, molybdenum, vanadium, niobium, tellurium, in a very special rotational shear structure is the best catalyst up to now for this reaction. Now, how does the Linde concept for this new process look like? And here I've brought a photograph. Maybe I do it like this. Yeah, this is a photograph of the pilot reactor at the laboratory in Munich. And this tube here, is the salt-cooled reactor, 8 meters long, to test the catalyst at the Linde site. The process as such works. You have some nitrogen feed. Doesn't work. I have to make it this way. There is nitrogen feed for the startup. Then you have water. You have pure oxygen, and you have ethane. So that's the feed. And this feed is very different to the feed that academia is using in the publications. This is one point. Why can't you use nitrogen? The reason is that you have to recycle unused ethane. And if you use nitrogen, you would just pile up nitrogen in the recycle. You cannot get rid of nitrogen. So the concept of Linde is to exchange the nitrogen, which you use during the startup, with water. So water is the inert. And you can, of course, easily remove water from the recycle. And then you remove ethylene, and you have the pure recycle. You can even remove the CO2, of course, and you have pure CO2. And you add pure oxygen, not air, and you add pure oxygen just in the amount that is needed to convert the amount of ethylene, or to make the amount of ethylene that you want. So that's the trick. And the trick is to be able to separate ethylene from ethane. This is done cryogenically, of course. You have to avoid that there is oxygen ending up. It would be very dangerous. So you add just as much oxygen here that at the reactor exit, there is basically 0 oxygen left. So your catalyst has to convert the ethane to ethylene that you want, and has to consume all the oxygen, still being stable. Now, if you look into this from an economic point of view, and we heard already that the economics are, of course, in industry extremely important, you can calculate that the return on investment is about 25% faster with the new technology as compared to a same scale cracker. Yeah. So this is really good news. And if you now compare the CO2 footprint, that would be the CO2 footprint for a conventional steam cracker operation. You see that we have 60% CO2 emission reduced with this new process. And if you capture the CO2 and utilize it, for example, for Coca-Cola or for making beer, it basically goes down to 0. And if you take green electricity for all the utilities, yeah, it's really 0 CO2 plant. That is possible. Now, that was the technology. Our task was to make a catalyst that can run in this technology. And so the second half of the talk will be on setting the scene for the catalyst development. And I will make it very similar. So I will not show you too much of what we did in the laboratory. So I will keep all these things for the later discussion. I will end with a list with the hope that this list can provoke your questions to me or to us. So, when you start such a project, you first have to do a very deep literature study. You have to understand in detail what is the knowledge that is around in the world. And and you can see that there was, of course, year-long, it was clear that oxidative dehydrogenation would be interesting, so people already very early worked on it, yeah. But there is one point in time, and this was 87 in the last century, where Mitsubishi published for the first time this complex mixed metal oxide. So it's a long, long time ago, and a lot of time went by and not a lot happened. And then you can see there was sort of a tsunami of patents and publications, and this is now going down this wave again. Yeah? But important, 87 was the patent filed by Mitsubishi. That means in 2007, this was expired and open for the public to use. And guess when we have started our project? In 2006. So because we knew that we would be able to use this, and this is exactly what my colleague meant with the freedom to operate. Yeah? When a patent is expired, you can use it. As long as this is active, you are not allowed to use it. So we have an excellent knowledge basis, and so this gives confidence that you can do something. Now let's have a little, and this is a very private view, on milestones in the literature. So maybe the first real important milestone is 78 in the last century. This was Thorsteinsson, also a very famous mixed metal oxide, because this mixed metal oxide is used for propane amoxidation, a very highly related reaction to what we are doing. And then, as I said, Mitsubishi was the first one with this metal oxide, then a second patent 6 years later, where they first described that this mixed metal oxide is active and selective in the ODH of ethane, giving already very nice selectivities, so close to the green box, not yet there. 10% in selectivity are missing, but already not so bad. Then BASF were the first to publish phase pure synthesis. Then, of course, a very important scientist, and who is here, he could really show for the first time that this special structure with these rotational shear planes is the important part of this mixed metal oxide for this reaction. And then Ueda maybe should also be mentioned because he managed to have a tellurium-free synthesis on a very small scale. So you can get rid of the tellurium, but this is not yet scaled up. So this is very, very tiny yields. So why, after so many years of research and development, why is this not commercialized yet? So I tried to put some points on this slide. Maybe phase purity is one of the reasons. Yeah? You have to make this catalyst more or less phase pure on a large scale. So that could be a problem that my colleagues had in the past. There might be detrimental phases if you cannot make it phase pure. Yeah? So you have, of course, secondary phases, and these secondary phases can kill your selectivity, or they can even lead to the fact that the catalyst becomes deactivated there, so they may act as seeds for phase transformations. Then you have a rather broad compositional space, so different research groups in the world have slightly different catalysts, or maybe not so slightly different catalysts, so the results they publish, they produce, are not really fully comparable. Then you have still insufficient product yields, especially the STY needs to be improved. And then, of course, catalyst lifetime issues, and we've heard how important lifetime is. Yeah? Such a plant needs to run, well, assume you have a plant with 4 trains, so 4 reactors in parallel. You should be able to run a reactor for years, so then you can exchange year by year 1 reactor. So lifetime needs to be 4 years. So what do you need to optimize? You need to optimize the M1 phase, so that is this mixed metal oxide. You need the optimum composition. You need the correct surface termination. Nanostructuring could be important, and we heard this morning by Beatrice. She showed how this is happening. And finally, large-scale synthesis is not known. So where are the problems? Yeah, as I said, Mitsubishi in '93, they used spray drying and calcination and had phase mixtures. Then BASF get rid of the phase mixture by dissolving this extra phase. Yeah? But this is nothing that you want to do on an industrial scale. Yeah? You make a very expensive oxide and you dissolve 20% and throw it away. No way. So it's clear to me why BASF never went down to commercialize such a recipe. A little later, my colleagues at the FHI, with whom we had a collaboration then, published the first phase-pure synthesis by a hydrothermal method. And this is the recipe that went into the AceNet project. And Vicente knows this very well because he was part of it. And this was the starting point for our development, yeah, this AceNet project here. And the synthesis is something that is very similar to what Mitsubishi did. And this is something that most of the people do. Yeah? So you have soluble compounds, you mix them in an autoclave, you make your oxide, and then you do the calcination in inert gas. But the problem, and I hope you can read it, these are very expensive raw materials. The production of vanadyl sulfate is very expensive. And even worse, telluric acid cannot be produced on large scale. Telluric acid is not available at all on a large scale. You can never make a ton of this catalyst using telluric acid because you cannot buy enough telluric acid. So it is impossible, it's simply impossible to make a catalyst this way on an industrial scale. So, and these were now the tasks, and that would be my last slide. You can read it yourself, but you know, the most important one, we had to develop an industrial recipe that can be scaled up to a ton. Then we had to develop a bench scale test, which is realistic for the Linde conditions. Because as I said, the Linde conditions are totally different to what the research has done so far. You have to fine-tune the industrial recipe again, because now we have different raw materials. It might be a different optimum compared to the soluble compounds. You have to secure the IP, so that is our own IP, yeah, protecting us from anyone else. You have to scale this up into the tens of kilogram regime, so that you have enough material to play around with. And at the same time, Linde built the pilot plant. And of course, if they build a pilot plant with a reactor of 8 meters, you need to have a couple of kilograms. That's clear. If you have a couple of kilograms, and if you want to go to tons, you need to register this oxide in Europe with a REACH registration. That means you need to do all the toxicological tests. Hundreds of thousands of euros that go down this road. And you don't have to do this in Europe, you also have to do this in the US and China if you want to sell the catalyst there. And so on, you have to, of course, develop a forming and shape for the real scale reactor. You have to develop a graded catalyst system, and this is maybe the most important part. You know, consider you are an ethane molecule, and you travel down the pipes to the reactor, and you will see the first catalyst. Yeah? You will be either converted or not, but if you go down the bed, you will see that the gas phase around you will change centimeter by centimeter. So the catalyst that can operate with the pure ethane oxygen feed at the top is and cannot be the same who has to work deeper in the bed. So you need to develop, in our case, 3 different catalysts that can cope with the different gas compositions and the different temperatures. It's an integral reactor, so that means you will form a hotspot because of insufficient heat release, and this you have to account for, and you have to make your catalyst. Yeah, and so on and so on. You need to have the sustainability screening. This is nowadays a must, so we had to do this too. We had to scale up into the ton regime so that we could feed information into our engineering teams. And for that, you need to explore all the equipments that are usable in principle, from the autoclaves to filter presses to I don't know what. And you have to explore all of this to know which equipment is the best. And then having done so, you know exactly how you make your catalyst. You have to make the freedom to operate, because then you know the process, how to make it. And then you have to check whether there is IP out there that might not allow you to use one piece of equipment. Because if this happens, the whole production road, you can forget about it. And then, in the end, you have to transfer this recipe to operations with the QC measures and so on and so on. I will not give you any more details here. You can ask me afterwards, and I hope I promoted a lot of questions that we will receive here. Thank you very much.
Thank you, Gerhard, for your interesting lecture. Also explaining us tax to catalyst commercialization, another good example. And as you see, different tax are not so different, both in Clariant and in Johnson Matthey. They are very, very, very similar. There are many similarities. Then you have already prepared, then
it's done.
You have the floor.
Thank you. So first of all, thank you very much for inviting me today to this around the table. Thank you to Maria Angeles and Luis. And well, so there will be no science in my presentation, and I will take a step forward from what was presented before, and we look what happened, some aspect of what happened once we have developed a catalyst, manufacturing, and we use it. And the purpose is to improve the sustainable catalyst cycle. In fact, sustainability is a key corporate value for nearly all the company. And if we look to the triple bottom line concept, there are three pillars that are profit, of course, but also the preservation of the planet and also people, preservation of people. And companies have to deal with these three aspects in order to evaluate their impact and to make a sustainable development. And of course, the catalyst industry is no an exception. Through its expertise, Eurecat is fully committed with this approach. And if we have our first starting point, that is the fresh catalyst, that is developed and manufactured, he needs to be activated and conditioned before to be loaded in a reactor, then is operated. And when the activity is slowing down, reactor is shut down, catalyst is unloaded. And at this point, what we have to deal with the spent catalyst, we can have a different action, some segregation that allowed us to separate the catalyst that can be in some way reused after a step of restoring the activity, so he goes back in the cycles, or if not more useful, we have to find ways to valorize it. And Eurecat is offering services in all the blue box that you see here. And today, I just give you a few examples of some of them. Okay. Okay, so we go back to the triple bottom line concept, and we start to look to the aspect of viable. That means we have to make profit, but at the same time, we have to preserve the planet. And how we can do this? Okay, catalyst reutilization, of course, is a way to combine the two aspects. And we know that for reutilization of catalysts, we have several problems. First of all, the activation by coke that lead to a low activity. Secondly, the activation by poison that can be permanent loss of activity. And also the used catalyst inventory. That means that we have a limitation on the availability of catalyst. And finally, unloading in wet condition that make not possible the reuse of the catalyst. For each of these problems, Eurecat developed some solution. First of all, for the low activity of the activated catalyst, we can have regeneration or rejuvenation. And for permanent activity loss, we developed some segregation analysis so that we can choose the part of the spent catalyst that can be reused and the one that is not more useful. For the availability of catalyst, we can create a pool management of regenerated catalyst or resale regenerated catalyst. And to avoid the wet unloading, we have some techniques that allowed us to unload the catalyst without destroying. Okay, so looking to the regeneration, so we saw that the first problem was the low in activity, that activity that we can recover after regeneration or rejuvenation. We know that the regeneration on type, in the case of hydroprocessing catalyst, on type 1 catalyst can restore more than 90% of the activity. But when it goes to type 2 catalyst, in that case, only the regeneration is not enough to recover the activity close to the fresh. But in that case, we need an additional step that is called rejuvenation that allows us to recover 95% of the activity of the fresh. And yes, what is rejuvenation? Rejuvenation is a redispersion of the metal on the surface of the catalyst, and weakening also the interaction between the support and active phase, so that the result is typical 30% more activity if compared with simply regenerated catalyst. And Eurecat developed its own regeneration technology that is called eBoost, and that we can apply to almost all the hydroprocessing catalyst, type 2 catalysts. But catalyst reutilization is not only good in activity, saves also money, and it's good for the planet. Same model, if you compare the saving by purchase the fresh catalyst or purchase regenerated catalyst, customer can save 45% of money, and if he goes for the utilization of his own catalyst, the saving goes up to 70%. And in the meantime, the reutilization of catalysts reduces environmental footprint. And first of all, by using the catalyst, we minimize the landfill disposal, and after all, we reduce the CO2 emission, basically because we avoid metals mining and purification. And Eurecat rejuvenation technology leads to 60% lower CO2 emission for a rejuvenated catalyst if we compare with the fresh. Okay, but we can also push the system in order to maximize the catalyst reuse potential with a different scheme. First of all, a customer can send to Eurecat the catalyst spent that can be regenerated and loaded in the same unit, in the same refinery, or he can use in another, in a different unit in the same refinery, or he can create a pool of catalysts that he can use in one of the refineries of his network. Yeah, well, there are already many measures that work with Eurecat on the pool management. And okay, But to maximize the catalyst reuse, it's also a question of ensuring the loading best practice. That means labeling and traceability once you are unloading your reactor. And also, in order to maximize the spent catalysis recovery, Eurecat developed a sample as analysis segregation process that allowed to exclude the poisonous material and to maximize the quantity of catalysts to be reused. Okay, this is an example of a reactor with a two-bed reactor, and thanks to SAS evaluation, we saw that in the first bed, there was only a partly of the bed that was permanently contaminated by poison like iron, arsenic, and silicon, but there was at least 120 drams that meet the criteria to be reused. So in that case, the segregation allowed to recover, maximizing the recovery of the catalyst. But before to analyze the catalyst that has been unloaded, there is the unloading in itself. And this is also can be improved, and Eurecat provides a field service to improve the gravity, the unloading by gravity, and in particular, avoiding inert entry into the reactor and maximizing the catalyst preservation. How? First example is the carbo dump. In the case you have in the reactor the catalyst that is clogged and agglomerate, and so it's not anymore free-flowing, so you cannot unload by gravity. We developed a technology by CO2 blast that we can insert in the reactor from the outside. By the instantiation explosion of the CO2, the catalyst is unclogged and it becomes free-flowing. So we can, from one side, minimize the inert entry, because we don't need the people that to go enter the reactor in nitrogen atmosphere that is pretty dangerous, and eliminate also vacuum, jackhammer, and dynamite use. So that means that the catalyst is preserved, and so that makes a profit because you can reuse, maximum the use of your catalyst. And we have a second technology that is Ulticat that allowed to remove the remaining catalyst after the gravity unloading. And thanks, in this picture, I showed the snake that is remotely, how do you say? I don't have the word. By video camera, you can remotely control, okay? And with a vacuum system in order to take out the catalyst that is on all the corners of the reactor. So we saw that there are many opportunities to valorize the spent catalyst and to avoid what was the initial path, the traditional path of the catalyst. That means the extraction of the raw materials to make the raw materials so in order to manufacture the catalyst. And then once the catalyst is not more useful, just to go for disposal and landfill. We already saw that there is one way to valorize the catalyst is that the direct reuse, like regeneration and rejuvenation, that allowed to lower in the CO2 emission. But there are also more open loops. First of all, an indirect reuse, if we go for reshaping of the catalyst, and more open loops that if we go for recycling the metals, that means the metal recovery to create secondary raw materials from circular economies that can go directly in the flow of production of the catalyst. So go back to the bottom line concept. We talk about viable. I would like to make an example of livable. That means we preserve the people and the planet. And this comes to the dust exposure from catalyst handling. As you see here, there are pictures of emptying big bags in a hopper before to go up in the reactor and to load the reactor. And you see how there is a big dust. And as the catalyst contains nickel and cobalt, so this is really dangerous because give exposure to the personnel. So they need extensive protection and a complaint from a neighbor, and of course it's not good for the environment. And moreover, we know that the occupational exposure limit will be more stringent in the coming years, especially for cobalt and nickel. And Eurecat developed a new coating technology called InCase that is designed to reduce the dust formation during the catalyst handling and loading. Here, as an example of a picture of dense loading, so there is a machine here that distributes the catalyst from the top of the reactor, and you can see in the left the untreated catalyst, how it's foggy. And in the case of the treated catalyst, there is no dust formation. And so you have two benefits. One is the personnel doesn't have a risk to inhalate the dust. And the secondly is that you can follow up how the loading is going and to see if it's the catalyst is well distributed, so to avoid the risk to have a professional channel that will be not good for the activity. Okay, so the InCase technology is an encapsulation technology. That means that each particle is individually and completely encapsulated. And this is compatible with most of the catalysts and most of the form. Is stable, of course, without loss of function and without agglomeration. And there are no significant effects on the catalyst physical and characteristic properties. And of course, the coating is completely removed during the startup of the unit and doesn't have any effect on the product. So what we see that finally, we don't have to talk only of sustainable catalysis cycle, but cycles. There are different cycles, open loops, more closed and more open loops. And so the starting point that at the beginning was the fresh catalyst, indeed nowadays have to be enlarged also to catalysts coming from the circular economy by indirect reuse. And all these steps will answer to the problem of to make a process viable and livable. And I'm coming to the conclusion, takeaways. So making catalysts more viable and sustainable is one of the challenges that we face preserving our environment. So the reuse of catalysts is profitable and lower the CO2 footprint. And there are many options available to optimally manage the catalyst reuse. The new coating technology reduces environmental impact to exposure, the hazardous substrate. And finally, to meet all these challenges for tomorrow, we should take into account all that from the beginning of the development and the research of the design of the new catalyst. And this is my last slide, so I really would like to thank you for your attention.
Thank you very much for your presentation, Tiziana. This has been another different approach how to make more sustainable catalysts by limiting the activation and regeneration, reutilization, rejuvenation, and some other different possibilities. Then we have more than half an hour or around half an hour for questions, for comments, whatever you want. Please, when you are going to do any questions, say your name, your affiliation, and if your question is directly addressed to one of the presenters or is open to all of them. Okay? Then it's your turn. Vicente, go on.
I am Vicente Cortés from Institute of Catalysis and Petroleum Chemistry, CSIC in Madrid. Thank you very much for all of you, because this is an approach that usually when you are working in academia you are missing. And especially I consider relevant that you pointed out several problems in which we must be conscious in which level of development, technological development, we must start thinking of. I make a couple of notes that probably can bring some ideas to other people to do. One of them, for example, is that when we study chemical technology, it is said that the leverage of catalyst is very important because catalyst itself is very low cost of the process. Usually it's 2% of the total process. But in this case, it for me enters in a little conflict with the point that both of you, the producers, has underlined, that is the cost of big amount of catalyst to be produced. For example, we have been seeing in this conference many papers that people are using MOFs as matrix or sacrificial materials to start with the catalyst and have a good dispersion. Indeed, this is an extremely high cost. One limitation one of you has pointed out is that several of these starting materials are even not available. But even if they are available and they are not the most cheap, which is the real impact to use not standard techniques to the total process, if the cost of the catalyst is only 2%. This is one of my questions. And related to this is one thing that normally is missing in the people who are not coming from the chemical engineering academia is the part of economic aspects. At which level of research you think that academia researchers must start to think about the cost of what they are doing? And related to this, and with this I stop, I promise, is another matter. Innovation, besides all the technical problems you have pointed out, faces another problem. For example, as Gerhard has said, in the oxidative dehydrogenation, there is the process of to obtain acrolein that is based on bismuth molybdates, and the process is known from the 60s. But still in this planet, there are plants working with the cyanohydrine methodology because the cost of the plant is many years ago completely paid. How can be, how new innovation can fight this fact, economical fact? Thank you very much.
Ladies first.
Ladies first, okay. Thanks for that. Okay, so I'll answer the one about when the academia should start. I'm going to start with that one. When the academia should start thinking about costs. And I think in the fundamental research, you shouldn't be limiting yourself because of that. There is a lot of knowledge even that you can't get, even looking at materials that may be really expensive, or not available, but you won't be able to scale up, but you can extract a lot of knowledge out of them. So I wouldn't limit the academia in that sense. There are things that you may get a formulation for a specific process that it will work with a very fancy material, let's say, indium for methanol synthesis, for example. I hardly see indium villain scale up, but we can extract knowledge from it, what other material will have equivalent properties, or what combination of other materials could have some equivalent performance. So I wouldn't limit the cost, especially at those scales. No. Don't know if you have a different view on that. Okay. So your first question was about
the cost of no.
First question was, at which level of development you introduce the factor of economy? The costs, the impact of the costs.
The part of the cost, from the very beginning.
Okay.
So you wouldn't, in the industry, you wouldn't move, you wouldn't get to the concept without having a perspective of cost. Yeah, the catalyst is very cheap for the customer. It's a matter of risk versus benefit. So from the methanol synthesis perspective, from my experience, I'll put an example. So a charge of methanol synthesis catalyst in a large scale could cost 10, 50 million of pounds. It's a lot of money. But if the customer loses the production of 2-3 days of methanol, it's around that. So I may have a new formulation, which may be slightly more expensive. The customer could pay it. But if they don't want to risk it because it hasn't been proven enough, they're not going to go for it. So at the end of the day, to me, it's a balance of benefit versus risk.
And this comes in lines with my third question. In which way innovation can fight the fact that current old technologies are still being used because they are already paid?
Sometimes you need to prove that there's no risk, and in some cases, it's legislation what move processes that are, unsafe or unsustainable. That the legislation in the countries that what moved them away, and the way we can, in that case, we'll have to have something that is. When we develop, we can be a product that is customer-led or is a customer push. So we do, in that case, that we need to prove the customer that that's the way to go, that we have a good process that is economically feasible, is sustainable, etc. But in the end of the day, if we do things to make money, the customer also wants to make money, right? So
thank you.
I don't know if you have anything to add.
No, this is exactly the way it is. And coming to your last point, how can innovation push for step changes? I think the only way is that you prove with one demo plant, at least, that your new development is so much better that all the other producers have to go for it. Because, I mean, that's the way. Yeah? If you can, like in methanol, I don't know whether this is possible or not, but if you have a catalyst or a process that can make, I don't know, 10 tons more per day or 100 tons more per day per kilogram or something, maybe this is now totally stupid, what I'm saying, but then, of course, everyone will have to use it, otherwise they can shut down immediately. And so that's the way. And the problem is, as you said, for the cyanhydrine process, this is something where the plant is written off, so they can produce for free, so to say, and they have the cheap feedstock that is available in these countries, and as long as legislation is not closing this, it's for them it's an easy product. Yeah.
It's not easy. Sorry, go ahead, Tiziana.
And then we can also say that, yeah, there are many clients, customers that are really conservative. Especially, I don't know, for petrochemical or also customers like Indian customers are really conservative. So it's very difficult to go for a change for new catalysts if you don't have a list of reference. So first of all, you have to find somebody that is believing you and that want to take the risk and make the investment. And this is sometimes is really difficult and can stop things going on.
For example, you know, the case that I showed, the ODH of ethane, only becomes possible now because China increases the price of CO2. And because the price of CO2 in the off-gas is becoming so expensive now in China, people reconsider the fact whether they would invest in a steam cracker or not. And only because of that situation in China, they start considering building such a plant, especially because the return on investment will be faster than with a steam cracker. So it would not have been possible 10 years ago because the CO2 did not cost anything in China. Now it is. And the same will happen with all the other processes. Yeah? As CO2 becomes more and more expensive, industry has to move. And this is a very good example where legislation is needed because a producer will not pay for it without the need. Off-gas treatment, car exhaust gas converters, three-way converters, without the California legislation in '72 or when it would never have happened.
Well, we can move to another question.
Yo voy a hablar en español, si me lo permiten. Primero es agradecerles la presentación que han hecho ustedes, porque he visto que hay dos aspectos fundamentales en la presentación. Uno que es el I+D y el otro que es la parte comercial de recuperación de catalizadores. Yo la catálisis la dejé allá por el año 2000. Muchos de los chicos que están aquí a lo mejor ni habían nacido, pero yo trabajé toda mi vida en el campo de la catálisis y me ha recordado lo que era para un diseño de un catalizador todo lo que ha hecho y lo que ha presentado Mónica. Es decir, el escalado de cualquier proceso, desde los pequeños gramos de catalizador hasta tener una planta de demostración, por cierto, muy cara y aconsejable que esta planta de demostración esté en el propio proceso industrial para poder utilizar los productos que salen, o sea, la alimentación y los productos que salen del reactor, meterlos a producción. La pregunta que le hacía a Mónica es en el sentido de realmente el coste del propio proyecto se incrementa mucho con la planta de demostración. Esa es la primera pregunta a Mónica. A la doctora Tiziana, indudablemente yo trabajé en Repsol y uno de los grandes problemas que teníamos en los temas de hidroprocesamiento era no solamente la pérdida de actividad, sino la atrición que se producía de los catalizadores dentro del reactor y que aquello generaba no solamente una pérdida de actividad, sino una pérdida de carga muy grande por la ruptura de las propias partículas, normalmente extruidos de 1,5, creo recordar, milímetros de diámetro, y que aquello, pues, las propiedades mecánicas eran malas. En aquellos momentos se planteaba hacer regeneración in situ o hacer regeneración ex situ, con todo el proceso que conlleva la presulfuración de catalizadores como Onimo, por ejemplo. En ese sentido, ¿cuál es la tendencia que en este momento se está planteando dentro del tema de Eurecat? Y luego después al doctor Gerhard, yo recuerdo que nosotros teníamos una petroquímica que producía acrilonitrilo, catalizadores Sojallo y catalizadores Nito. Había una diferencia con respecto a los multicomponentes. Quiero recordar a un amigo nuestro ya fallecido, Bob Grasselli, que trabajó mucho en el desarrollo de los catalizadores Sojallo. Teníamos problemas en la planta industrial de acrilonitrilo por la vaporización del teluro. Y teníamos que meter teluro dentro, adicionarlo al reactor para mantener el contenido de teluro. Hoy en día no sé cómo está este tema de los catalizadores multicomponentes. Me gustaría que me pudiera también comentar algo. Muchas gracias. Perdón por hablar en español.
Could you understand? Not.
No,
So,
yeah.
then, well,
Roughly.
The main meaning, yes.
I will try
Yeah, same
to say
for
it,
me.
but first, Mónica, you can ask, you can answer your
Okay.
question.
¿Respondo en inglés o en español?
It's up to you.
Ok.
En español.
¿Ah? ¿Español está bien? Ok. Primero, no tiene por qué culparse en hablar en español. Llevo mucho tiempo que no me hablan en español, así que ha sido un placer. Con respecto a cómo aumenta el presupuesto de un proyecto con la planta piloto, mucho. Afortunadamente, una vez que se hace la inversión de esa planta piloto, se puede usar en múltiples proyectos. Y normalmente nosotros tenemos las plantas pilotos acopladas a una planta de un cliente. Y como usted mencionó, súper importante porque nosotros tomamos el gas que va al reactor de metanol, tomamos una parte de ese gas y la pasamos por la planta piloto. Entonces el catalizador estará viendo exactamente la composición con los poisons, con los venenos, exactamente que van al reactor pasando por esa planta. Y muy importante, que normalmente nosotros podemos después tener una descarga controlada del material que está en la planta piloto y mirar todas las propiedades mecánicas que usted mencionó que son muy importantes, incluyendo attrition, las pérdidas por attrition, attrition, perdón, y sí, de compresión y muchas las otras propiedades químicas y físicas que podemos ver.
La pregunta también era, ¿hay toma de catalizador en el reactor industrial para seguir el proceso del catalizador?
Es muy peligroso. Se hace al final, como es por ejemplo, el metanol, vamos a hablar del caso de metanol, está reducido. Apenas lo expone al aire, se oxida y entonces va a tomar el aire, entonces crea un ambiente en el que reduce la concentración de oxígeno y sería muy peligroso para cualquier persona y además compromete la integridad del resto del catalizador que está en ese caso. Entonces realmente no se hace. En reformado, por ejemplo, si llegan a hacer ese tipo de cosas, pues se puede controlar, pueden a lo mejor aislar un tubo, pueden hacer pruebas por afuera para mirar analizar cómo va el catalizador. Sí.
Okay, just as an introduction, Sebastian Vick was doing many years work on catalysis at the company Repsol. He was also the president, sometimes of this society, even when this society was previously a specialized group inside the Royal Society of Chemistry in Spain. That's the introduction. If I understood well, the question for Tiziana was something that also you mentioned. Is about in some of the processes they were working, there was the activation, but not only by coke or sintering, also by attrition of the catalyst, and then
some plugging in the reactor.
So what is your opinion about that? If also this is important, something like that.
Yeah, well, of course, this comes with the development of a catalyst that is more resistant at first. Yeah, so from the development of new support, but we are also personally working with the coating that I showed you. We are also in Eurecat working on some coating in order to try to fortify for example, the extrudate in order to make more resistant. But in the aim to be more easily regenerated and rejuvenated. Okay. But of course, yeah, if you have the reactor that is plugged because there are fans, the best things to do is to unload and to separate, to make some segregation of the catalyst in order to make some length grading, to choose the part of the catalyst that is without the poison and to a good length, and in order to be regenerated and reloaded in the reactor. This is typically a service that we do when we receive spent catalyst.
Okay. And the third question for Gerhard, I think Sebastian was working at those times in the production of acrylonitrile, and the catalyst, I think it was based on tellure. And they had problems with vaporization of tellure. He's asking about how is managed this today, or if there are other different catalysts, or
Okay.
what's your opinion?
So acrylonitrile nowadays is made through catalysts without tellurium. So I don't know whether this problem still is present. Probably not, because the catalyst system is different. So it's a bismuth, molybdenum, nickel, iron, magnesium, potassium, sodium mixed oxide, and does not contain tellurium anymore for the acrylonitrile. In our case, the tellurium volatilization, of course, is something that is discussed a lot in the literature, but if you fine-tune your recipe to such a level that you only have the minimum amount of tellurium that needs to be there in order to stabilize the structure, you will not lose it. So we had runs for 2,000 hours in a pilot reactor without losing tellurium. So it is really only taking place when you, A, have too much of the tellurium, and B, if you run the reactor in a wrong manner. Then it can happen.
Perfect. It's okay, Sebastian? Okay.
You're welcome.
Then another question?
Yes, I have a question.
Sorry.
I am Jesus Lázaro from the Spanish company of oil Cepsa Chemicals. First of all, thank you very much for your talk. My question is about the business case. And my question is how to manage in your company the balance between the bureaucracy of the business case and the opportunity of the research. Because sometimes you go with an idea and you need a value proposition, you need the market, you need the revenues, and in the very early steps of the catalysis, it's very difficult to know what is going to be your client, what are the revenues in the future. So how do you manage this balance between these facts?
Mm-hmm.
Wanna go first? Or?
Ladies first, always.
Again.
Always.
It's too easy.
Easy for me.
Ladies first. It's not that easy to manage because you rely a lot on the information and the predictions you make. So you have to look at how the market is going to evolve And there are a lot of assumptions behind that. And then you also will have to look at your customer base and how much of that market you think you're going to be covering so that you can have some sort of numbers for your business case. In all cases, and there's always a lot of assumptions, so it's not an easy task. But you still need to go through that exercise and get much precise numbers or predictions that you can have. Sometimes we also do fundamental research. We may also work on things that don't necessarily have a big business case attached to it. So in Johnson Matthey, at least, we have corporate R&D through our technological centers, where we look at all the fundamental or core projects. And on those projects, you look at very long term. And sometimes you don't really know what the really long term is going to be, but you still need to look at things that may materialize in many years, because otherwise, if you don't work on those things, when the time comes, you are not ready. Then we also have R&D attached to like businesses, which is where I work, which is a more applied research. And if I don't have a business case, I'm not going to have a go ahead, but I can still ask to have a project in the core business and still do some fundamental research for something I see that is going to be a need. Does that somehow answer what you were after? I don't know if you want to add something.
Yeah, maybe this is very, very similar in our case. The only thing that I can add maybe is, again, the example that I showed to you today, because we decided in 2005 that we would go into this class of oxides. And it was not because back then it was clear that the ODH of ethane would become interesting. This was really beyond the horizon in 2005. But because we understood that having a fundamental knowledge on this type of molybdenum-based mixed metal oxides can be a platform for many reactions. And you know that the same oxide, slightly different composition, can be used for propane oxidation. Yeah? So, and if you fine-tune it further, you probably could use it, and no, not probably, but you can use it, and this is a commercial example, for acrylonitrile. Yeah? So it is really a platform, and you could, for example, I don't know, I did not try it in the past, but you could add copper to it, you could add bismuth to it, you could add many other things to it, probably fine-tuning it to any other reaction, partial oxidation reaction that you may want. So this was the fundamental assumption that we had, and this is really free research. So our board of directors gave us the money to cooperate with the Fritz Haber Institute on these questions. We had the AceNet project where Vicente was involved. We were not really deeply involved there, but our job was only to scale up the final good catalyst. But yeah, so you can have such research where you think you have something that may be important in 20 years. Yeah, so that is exactly such an example. Now it's almost 20 years later from when we started, and we have something that is going to be commercialized. Nobody would have known it. And even 10 years ago, it was not foreseeable that this would become a technology, as I said, only because of the CO2 price. It may become one. Yeah. So both you need to do, and in more market-related projects, we do the same exercise, business case, very early. So even when you have a first idea, you have to present a business case. And that is why you have to look into the raw materials. You cannot go for fancy synthesis, because this is never going to be a business case then, and so on and so on. Yeah. But only the business case can prove your superiors that this idea may fly. Yeah.
And what maybe I wanted to add is that a business case, it's also important, not only when you do fundamental research, when you have to develop a new catalyst, so you have to make a lot of effort in developing a new catalyst, but also when you have a simpler request. For example, in my case, if I have a client that comes with a catalyst that needs to be activated in a way different from what we are used to do, but is, for example, a catalyst for a niche market, well, my boss come to me and said to me, first of all, which is the business case, how much can you sell it, and how much money can we earn, before to go to talk with the research and development department in order to start some study. But sometimes we can also decide, okay, we will invest some research because we will increase our knowledge. And so it's worth, also if the business case is not really solid, we go for, because we know that we'll acquire some knowledge that maybe we can use in other situations.
Thank you very much. I will talk with my boss about this topic with your opinions.
Thank you. Any other question? No more? No.
Juana Frontela, CEPSA Research Center. Thank you for the roundtable. Very, very interesting, and congratulations, organizer, for this interesting proposal. My comment or my personal reflection is that when we, at the research center, we compare catalysts because we give this technical information to the refineries. When we compare catalysts, we measure two things. One is the initial activity of the catalyst, so at the very starting condition of the catalyst, and later we try to measure the stability. For this purpose, we carry out the activation test, as you mentioned, Mónica. But sometimes I'm afraid, and we are not really in real condition, because during the real test, during the real run, can happen many things. You can have temperature upsets, I don't know, a shutdown, changes in the feed. So for us, it's important to know what is the theoretical stability of the catalyst. But later on, we realize that the real life is not as such. So what is your opinion of that? Do you use as starting the activation test is a very good information, theoretical information to compare the stability, or do you consider this is real?
Okay, so in my experience, it's one of the biggest challenges, because you sometimes can't simulate plant upsets, as you mentioned. Specifically for the example of methanol, that's where the pilot plant is our best ally, because the pilot plant will have the same upsets or similar to the ones that the big reactor is going to see. So we normally validate all our stability tests against a pilot testing. And those have been developed based on that. And you need to use a combination of factors, how you said, is the initial activity plus stability plus resistance to poisons plus mechanical physical properties over time, etc.
Yeah, we use the activation test, but for example, the resistance to poison or to coke or to high temperature is different. One catalyst is better than other. So if the unit suffer an upset of temperature, for example, the deactivation rate changes dramatically. So for sure you will need a catalyst more resistant to temperature, but at the beginning you don't know. So it's a good tool, but it's not the real life, in our opinion.
Yeah, but real life will be 4 years. So
much more complicated.
Yeah, there's always a compromise, right?
Okay, thank you.
But what we can do also sometimes, for example, take advantage on the analysis of spent materials. So you have a real catalyst that is unloaded from the unit that worked for, I don't know, 1 year, 2 years. You have a certain residual activity with content of contaminants. And so this can help you in order to tune a pilot testing that can mimic, in a way, the deactivation that you can see in a reality. And so this can help.
Absolutely, I agree with you.
To find a
the
protocol.
analysis of the spent catalyst gives a lot of information about the stability. Yeah, for sure, this is a good practice. Thank you.
And this is really fundamental.
Fine, we have time for 1 or 2 last questions. Perfect, Anthony.
Thank you for the presentations. I'm Andoni Choya from the University of the Basque Country. And this is a question related to one that was done before, and it's mainly directly to Dr. García Diéguez and Dr. Mestl, because they have talked about this road from the model to real catalyst. How much would you say that the industry trusts the research that is made in academia? Now, I'll rephrase the question. If there's a researcher that has got this catalyst, they have developed this catalyst, and they are in the point where they have to jump from that model to that real catalyst, would you say it's better for them to try and contact the industry around them, or is it better to try to get that catalyst to work by starting up their own company, for example?
This is a very political question. You must be careful. In this audience, we're gonna be crucified.
In my area, I have seen everything from the academia. From
I'm
like
sorry if I got you into trouble. I'm sorry.
No.
With the question.
It's fine. I think sometimes it's very important. There are a few things that are normally neglected in the academia when looking at methanol synthesis, and one of that is selectivity. Right now, with all the boom of CO2 to methanol, there is a lot of focus on selectivity to CO. And in the real process, it's not important. Since the reaction is limited by equilibrium, you're going to have a loop, so a recycle. So everything coming out of your reactor is going to, a fraction of it is going to come back. So the CO you form is going to come back, and it's going to be good. It's going to help you. So, and the actual concentration you see in that converter is not 3 to 1. Really, so it's not going to be as much CO2 as the people tend to study in the academia. So that the catalyst is going to be seen much less. I know it's sometimes difficult in the academia to replicate exactly the conditions, but sometimes it's, there is a disconnect. So try and sometimes to talk to the people from the industry. It could be good because you can then test the materials closer or look at aspects that are actually really important. So for us, it's more important selectivity, but not to CO, to ethanol. We form tiny, tiny amounts of ethanol, ppm levels, but that's enough to really change the size of the distillation size of the process. You measure methanol, it's going to come with water and many other organics, so you need to separate them through distillation. Just for a bit of ethanol you make, you lose a lot of methanol. So, and that, a lot of that, byproducts in very tiny amounts are much more important than any CO you form for example, CO2 to methanol. So, we get a lot of knowledge from the academia as well, like basically more on the fundamental stuff, but not so much on the evaluation of the catalyst on real conditions, because either the systems that academia got, can't reach the pressures or the concentrations we can in our, or they don't really have enough awareness to know what the issues are. So I'll definitely encourage people working in a specific field, if they come across with someone from the industry working on the same, to ask those sort of questions so that you focus your research on what is really important.
Okay.
Is that what you were after?
Yes, basically that. Yes, that when you come to the point where you have to scale up your catalyst, is there any way to not any way, but what I was thinking is it better to just keep working by yourself or try to collaborate with your environment? Because what it looks like is, I'll ask bluntly, okay? Is there anybody going to hear you or try to understand what you're doing, or they are just going to ignore you and say, you know,
No,
we are working on our things, I don't want to hear from you?
No, we hear you. I can tell you. I haven't said no to anyone that has come to me and tell me, can you test this on the methanol synthesis conditions? Yeah. What is it in it? Yeah, I can test it. We'll put it in one of our labs. But I don't hear to many people, but if they come to me and tell me, you know, could you do this for us? We have never said no. If you know.
That sort of answers my question, yes. Thank you.
Yeah.
I agree with Mónica, because in our case we have some catalysts, and just speaking to some people specialized in the same process at Johnson Matthey, they told us rapidly, send to me your catalyst, and we can test your catalyst in our plant at other conditions, more at high pressure or different temperature, or even, no problem with that.
Yeah, we may not do it straight away because it may not be our priority, but I've never said no, if that makes sense.
Your point?
Yeah, maybe to add, very, very similar, very much the same. We even have always at least 1 to 2 PhD theses in the research department, or currently even in my department, where we especially look into the scale-up. Yeah? Because this is obvious that there must be a translation from the academic research to somehow into the industrial environment. And the scale-up, of course, into the kilogram regime is the thing that academia typically cannot do, because you do not have the equipment, and the equipment is extremely expensive. And a priori, it's not clear that this one piece of equipment does the job right, so you need a series of different machines in order to do tableting, to do extrusion, to do filtering. There are many different filter options that you have, and so on and so forth. So, but we always invite in academic researchers to join us, and we always have students in our laboratory in Munich that do such kind of work. Yeah, so clear. It should fit to the purposes of the company, so that's also obvious. If this is in the area of interest, which is in Clariant's case quite simple, because we have thousands of catalysts, so it's hardly impossible not to be in our interest. So, but then, yes, it's always possible. We have sort of an open lab for academic corporations. Yeah, like you said, you're really invited.
No, nothing. A very short final question, if any. If not, well, thank you very much, Mónica, Tiziana, and Gerhard, for your excellent presentations. Thank you all the participants for your questions, and all people at the room at this time, because your resistance to be here listening, and congratulations to the organizing committee,
yes,
because I think that this new activity has resulted successful. I think, in my opinion at least, then we can repeat for next editions. Then thank you very much for everything.
Special help to Luis.